Okay. Hi, everybody. Good evening. Hope everybody's doing good. So, yeah. So, I see only four of you. Is there any exam going on today, people? I mean, do you have any
No,
exam?
sir.
Then why is the strength so less? Is it a mass bunk which you guys have planned?
Can I just ask them? I know two of them from my class. So
Yeah,
can
yeah,
I?
yeah. Sure,
Yeah.
sure. Like everybody can do that. If you know some of your friends, like please ask them to join soon. Right. So maybe we'll maybe wait for 2-3 more minutes for your friends to join. So in school, in all of your schools, which chapter is going on in chemistry?
Redox reaction they have started. We are in
So
halfway.
okay, so they have completed the periodic table, chemical bonding, all those things.
Yeah, sir.
Yes.
Okay, so periodic table, chemical bonding, and then they have started redox reactions. Okay, so your I think the first term, like they're separated into two terms, right? The first term exams will come in December. Is it like that?
No idea, sir.
No idea. Okay, great. Okay. So it's 5:35. So we have five people, including me, six, right? So maybe I think we'll start, right? So guys, since the strength is very less, like the class is supposed to be for 1.5 hours. Can we do it 1 hour, or you wanna do? Is it if it's okay for you? It's okay for me. Like, what do you wanna do? You wanna do 1.5 hours, or we'll do 1 hour and finish it?
Anything is fine, sir.
Anything is fine. Okay, so let us continue. Maybe if the class goes really interesting after 1 hour, then we'll continue. If not, we'll stop it right there. Okay, we'll just decide at that moment. Yes, Raghav, you want to say something?
1.5 hours.
1.5 hours. Okay, fine, cool. So we'll see. Okay, so let me share. Am I made the host? Am I the host? Guys, no, right?
No, sir.
That is also a problem. Oh, wait, I will text excellent people regarding this. So yes, I am with the host now. I think I can start. Let me share my screen. Okay, so we were continuing, we were seeing periodic table, right? So if you can remember, like we were talking about, I think the first class we talked about how exactly the period table is structured, how is it constructed, what are groups, what are periods, what are the valence electronic configurations of each and every group, right? And then went on to see if I give you group number, period number, how will you find the atomic number and vice versa. If I give you the atomic number, how will you find the group number and period number? Right? And then we went on to see this atomic trends, right? So in atomic trends, we saw first one was atomic size, how it varies down the group and how it varies around the period, right? And then we saw for ionic species, say if I have a cation and a neutral atom, which will have higher size. So which will have higher size when I compare Na plus and Na, which will have higher size?
Na.
Na, right? So always remember the cation, the apparent atom will have more size than its cation, right? And it's the reverse is true for anions. The anions are bigger in size when compared to the parent atoms. Okay, right? And then as you add, like say it goes on very good. Like say this goes on Mg2 plus will have lesser size than Mg plus, and Mg plus will have lesser size than Mg, right? And the same will be true for your negative ion. Say O2 minus will have greater size than O minus than oxygen, right? So this holds good, right? So then we went on to see this about ionization enthalpy, right? We know what is ionization enthalpy now, the modern definition, obviously, right? So it is the energy required to take out the electron from valence shell, right? Now, why do we have to spend energy? Anybody can come up with an answer for that? Why do we have to spend energy taking out the electron from valence shell?
To overcome the nuclear charge.
Correct. To overcome the nuclear charge, the nuclear force of attraction, right? To overcome that, you definitely have to spend some energy to break that force. Okay. So, and we saw how it varies down the group, along the period. Now I told. Yeah. So, how it varies down the group, it's gonna decrease, right? Because what happens when I go lithium only one shell, potassium two, sodium two shells, then potassium will have three shells. So obviously the electron goes far and far away from the nucleus, right? So it is more and more easy for me to remove the electron. When I say more easy, lesser energy is spent. That's what it means, right? So that's why we say down the group, ionization enthalpy decreases, right? Now, same thing, when I go along the period, the opposite happens because the atomic size decreases. Like when I go from lithium, beryllium, boron, and all that, the size keeps on decreasing, right? So when the size keeps on decreasing, obviously the valence electron is closer and closer to the nucleus, right? Thereby, it makes it more and more difficult for us to remove the electron. So from left to right of the period, ionization enthalpy decreases. Okay, right? I'm sorry, increases. Across the period, ionization enthalpy keeps on increasing. Is that fine? And here there are little more important things. You have to be very, very careful with respect to this half filled and fully filled configurations. Half filled and fully filled configurations. right? So now I told you along the period, there is no problem. But when I go for this carbon, nitrogen, oxygen, obviously nitrogen will have more ionization energy because along the period, that's what we predict along the period, the ionization enthalpy increases. But when I compare oxygen and nitrogen, again, nitrogen is going to have more ionization enthalpy because I know here I'm going to have 2p3 configuration, right? P2P3 is obviously half-filled configuration, right? So that is going to make it more stable, right? Thereby, I will not be able to remove the electron after this, right? Now, this half-filled and fully filled things can work for ions also. Hope you remember we solved. I asked you to find I asked you, I think it's for carbon, nitrogen, oxygen, fluorine. I asked you to arrange them in the order of the second ionization energy. If you can remember, we solved that question, right? So for second ionization energy, first of all, you need to have the monopositive cations after removing one electron. That is, when you spend the first ionization energy, one electron is removed, right? So now you have these things. Now for them, you have to check now, like you have to write the electronic configurations. And again, you will see that oxygen is going to have 2p3. Oxygen plus will have 2p3. So again, there you will have some problems. Okay, so you have to be very careful with this. You have to be very, very careful with this half-filled and fully filled configurations when it comes to ionization energies, right? So I think this is what we saw last class. Anything else you saw last class? Anybody wants to add some points? Okay, fine. I think this is it. This is what we saw last class, right? So moving on, today, the trend which you're going to see is electropositivity, right? Now, fine. Now, this electropositivity can be clubbed with so many other atomic trends. Say, for example, I can club it with something called as metallic character. I will connect all the dots, don't worry, how electropositivity is connected to the metallic character. It can also be correlated with reducing nature. Right now, obviously, when I say reducing nature, it is going to reduce something else, right? So, like most of your schools, redox reaction started. When I say reducing agent, when I say reducing agent, right? Now, reducing agent obviously is going to reduce something else, right? Now, the question is how it does it is the question. Anybody wants to answer me this question? How a reducing agent reduces something else?
They undergo oxidation and reduce the.
Exactly, right? So they undergo oxidation. So it's like a sacrificial kind of thing which they do, like not only reducing agent, even oxidizing agents, right? So if in a reaction, right, if in a reaction, say for example, I have A plus B giving products, we will again see them when you go for a redox reaction, but still just giving you a thing here. So when I say, for example, A is oxidized and B is the one which is getting reduced, right? Now, if I ask you, which is the oxidizing agent, which is the reducing agent, like blindly you can tell whichever is getting oxidized is the reducing agent and whichever is getting reduced is the oxidizing agent. So in this case, A is getting oxidized, so that is the reducing agent. I write RA, reducing agent, and this is getting reduced, B is getting reduced, so I'll call it as OA, that is the oxidizing agent. Okay, so now I have told you that I am clubbing electropositivity, metallic character, reducing nature. Now, since I'm talking about the ability of the element to be a reducing agent, again I repeat, since I'm talking about ability of the element to be a reducing agent, I can also say that I can even talk about ability of the element to get oxidized. Is it not? Only if it is getting easily oxidized. Excuse me. Yeah. So only if the element is easily getting oxidized, then I can tell that it will be a good reducing agent, because a good reducing agent has to get oxidized very easily. Is it not? So all these things can be clubbed into one category, right? And everything like along the period and how, across the group, how is it going to vary? Is going to be same, because everything is connected. Everything is almost there, like electropositivity. Okay, fine. If I tell you what exactly are these, if I just tell you electropositivity and what is metallic nature, then you'll be able to easily understand. Okay, right. Now, the term electropositivity, right, what it says is that, so see, you tell electropositivity, like, so from the name, what will you understand is that it is the ability, or I would say this is the definition of the term electropositivity. It is the ability of the element to form a cation. As simple as that. Right? It is the ability of the element to form a cation. Right? That is what you mean by being electropositive. What do you mean by electropositivity? Means it is the ability of the element to form a cation. Right? Electropositive means positive charge. Is it not? Now, or I can, in also in other words, how will you form the cation?
Losing
Obviously
electron.
by losing electron, right? So I can even tell this definition in a little modified manner. I can tell that it is the ability of the element to lose electron. As simple as that. Because obviously if I have to form a cation, obviously I have to lose an electron. Correct. So either way, like what to say, it is the ability of the element to form a cation, or it is the ability of the element to lose electron. Both are correct definitions for electropositivity. Okay, right. Now you can now easily understand how is it going to now. Okay, now generally, now why do I call it as metallic character? Because we say generally when you're 10th class metals and non-metals chapter, you would have learned one of the properties of metals is that metals are what? Electropositive in nature. Is it not? Metals are electropositive in nature. Basically means what? Metals will only form cations. Metals generally will not form anions. It's not like metals only will form cations. Very rare cases, metals can also form anions, but in general, right? Metals are electropositive in nature. That means if they form an ion, it will always be a cation. That is what it means. That's why electropositivity and metallic character are same. Okay, now you look into it. Now, if you understand this, ability to get oxidized, obviously reducing nature is again connected. Right. Now, tell me, since your redox reaction chapter is over, tell me, define oxidation in terms of electron.
Addition of electron.
Addition of electron. It is loss of electron. Okay. So when I say an element or a substance is getting oxidized, that substance would have lost electron. Okay, I'll give you this. Oxidation is loss of electron. Reduction is gain of electron. Okay. Okay. Please remember this again. We'll look into all these points when we go for redox reaction chapter. But for now, these are required for you to understand these concepts also. Okay. So oxidation is a process where substance loses electron, and reduction is a process where a substance gains electron. Okay. Right. Fine. Now this we understood. Now you can understand how the cation ability, the ability to form a cation or ability to lose electron. This is where the trick lies, right? So if the element lose electron, what is it? Obviously, it is getting oxidized. Right? That's what I told you here. Oxidation is a process where a substance lose electron. Is it not? So now when I say ability to lose electron, obviously it is the ability of the element to get oxidized. Hope you're able to correlate the points, right? Oxidation is nothing but loss of electron. Okay, and obviously if a substance is getting oxidized, and that naturally will become a reducing agent, and that is why we call it as a reducing nature. Understood? Right? So all these points are connected now, right? Is there any questions anybody want to ask me how all these 4 points are connected? Everybody understood? Is it okay, people?
Yes, sir.
Yes, sir.
Okay, I hope everything is connected. Electropositivity, metallic character, ability to get oxidized, and reducing nature. All these are connected now. Okay, now that we understood all these 4 are connected, now we'll try to understand how are these things varying down the group and along the period. Okay, right? Now I can easily speak in terms of ionization enthalpy, right? Can I tell electropositivity and your ionization enthalpy are inversely related? Can I tell this point? Can somebody give an explanation for the thing which I wrote here? I'm telling you, ionization enthalpy and electropositivity are inversely related. Can somebody give an explanation for this?
Yes, sir.
Yeah, go on. Anyone?
Yes, sir. If electropositivity is more, then the electron can be easily lost, and hence the energy required to remove the electron will be very less.
Exactly, right. So now, how will I be, first of all, if the element has to lose electron, it cannot do on its own, obviously, because the electron is tightly bound with the nucleus, correct? So some amount of energy has to be spent, right? So now, when I say the element has high ability to lose electron, so indirectly what we are telling is the amount of energy spent in removing the electron process is very less. That is what we are trying to say, right? So element with very high ionization energy, obviously for it to lose electron, lot of energy is spent, so electropositivity is less. Okay, so this point, if you understand, then seeing how the thing varies along the period and along the period and where down the group is very, very easy. Whatever happened for your ionization energy, the exact opposite will happen for electropositivity. Right? Okay, so can I directly conclude now? Down the group, electropositivity increases because I know ionization enthalpy decreases down the group, right? So if I ask you lithium, sodium, potassium, which is the arrange them in the order of electropositivity, obviously you'll arrange like this. Potassium is more electropositive than your sodium, and sodium is more electropositive than lithium. Same goes with your other groups, say beryllium, magnesium, calcium. Calcium is more electropositive than magnesium. Magnesium is more electropositive than beryllium. So this is understood now. Okay, now this you understood, right? Now in your 10th class, in your displacement reactions, hope you remember that one of the type of reaction is displacement reactions, right? In displacement reaction, we talk about reactivity series. Correct, right? So if we say that if I have, okay, answer me this question. I have copper plus HCl. What is the product form? If I add copper and HCl, what is the product formed?
Sir, no reaction.
Exactly, right? The reaction won't happen. Why it won't happen? Because if I compare the reactivity of copper and hydrogen we say is more reactive. Okay. Now, when I say more reactive, we are talking nothing but the electropositivity. Right? More is the electropositivity. Obviously, see what you're understanding, right? If I bring in little more, little technical words, if I use this term, reducing nature, okay, then it will make more sense. Now look at this, right? Or we talk we don't have to confuse ourselves. We can talk only in terms of electropositivity. When I basically say reactivity, again, reactivity of a metal, obviously. When I say reactivity of a metal, it is nothing but the electropositivity. Remember this. Okay, it is nothing but the electropositivity. Okay, now, so that means this reaction won't happen because copper is less reactive than hydrogen. And you can easily understand now, if you like now down the group, I said it increases. So obviously along the period, it is going to decrease, right? Along the period, it is going to decrease. Okay, so obviously hydrogen is at the top, right? Copper is somewhere here in the periodic table. This is hydrogen, this is copper. So obviously down the group, it increases, right? Along the period, it decreases. So obviously there have been a lot of decrease when it comes to copper. Okay, right. So anyways, so this you have to understand. Down the group, it increases. Along the period, it decreases. Do not mug it up, for heaven's sake. Please do not mug up atomic size. Down the group increases, along the period decreases. This thing, ionization enthalpy, down the group decreases, along the period. Please do not do that. Please, for heaven's sake. We are all science students, right? I mean, including me, we are all science students. So whenever you approach a question, you should approach it scientifically with logic, not because someone asked you to mug it up. Okay, for everything I said, see how much time I spent on explaining what is electropositivity, how is it related to metallic nature and all that. This is just a point. This I spent not even a minute. This is very easy. This is just an outcome of our discussion. Okay, so anybody, like, tell your friends also who have missed this class, do not mug it up. If you're gonna mug it up, yes, you will get marks. Like for the exam point of view, the marks point of view, yes, you will get marks, but that is not the end goal of it. Okay, we are all science students. You are here to learn science. Learning and getting marks are not the same thing. Okay, please be very careful with this, right? Like it will be like if you do that, it will be temporarily very beneficial, right? But say if at all you're not going to mug up, and if someone asks you like 10 years down the line, say I want to know, like say you're okay, may you become father and you become mothers, and your daughters and sons ask you, hey, how is it, like why is it that the copper and hydrogen HCl reaction is not happening? If you were to mug it up, definitely you will not answer this question. But if you have really scientifically understood the logic, then definitely, even though you were not in touch for all this while, you will be able to answer those questions, even after 10 years, 20 years. That should be the goal. Whether you end up working in science, whether you are going to become scientists or engineers or doctors, that doesn't matter, right? But these are some of the common basic things which should be known to everybody for that matter. Okay, right. Anyways, fine. So that's about electropositivity. Anybody wants to ask me any question regarding this? Okay.
Sir, I have
fine.
a doubt.
Yeah, tell me.
So, what do we mean by gaseous atom?
What do we mean by gaseous atom? The name itself tell you atom and gaseous phase. Any specifically you want to ask why this came up to you?
No, sir, because in definition of ionization energy, at the last like even in our NCERT books, it is specified like.
Makes sense. Makes sense. I'll come to that point. That's a nice point. Actually, that's a important point which I missed. Okay. Now, please understand, ions, right, can be formed only in two of the states. Okay. Right. I would say not. Okay, we can call them as states. Okay. One, ions can be formed in gaseous state, or ions can be formed in aqueous solutions. Okay, in solid state or in liquid state, ions cannot be formed. Okay, now the reason is very simple, because in case of solids and liquids, the atoms are very closely very constricted, right? If I have to remove an electron, right? Say it is not going to depend only on one particular atom where I'm removing the electron. Since so many atoms will be close by in a solid and a liquid, right? This atom will influence this atom, and this atom will influence the next atom. The next atom will influence the next atom. So we will not be able to get the correct ionization enthalpy value, or for that matter, we will not be able to understand the true nature of the element for that matter. Hope you understand what I'm trying to say. Since one atom is in the same atom only, even the sodium atom and sodium atom, but still, I want to find the ion forming ability for an individual atom. Then only all the other things will come properly, isn't it? I know in gaseous phase, obviously the interatomic distances, right? The interatomic distances are very, very high. Okay. In case of aqueous solution, there is an entirely different story. We will come back to that in chemical bonding. Okay, we'll study about hydrogen bonding and stuff, right? At that time, this will become very, very, very clear. Now we don't have to spend time on this. Okay, so now this gaseous atoms are very, very important. If you are going to form an ion, right? If you want to form an ion, the atom or the element should be in its gaseous phase. Okay. Now, why? Now, especially for ionization enthalpy, in your book, actually, I forgot to say, it should be, I told you that valence shell of an atom, it should be valence shell of a gaseous atom. That should be the perfect definition. Now, why? Because of the reason I said, because one atom, say if the atoms are very, very, very close to each other, this atom will influence this. So the ionization enthalpy value you will get, obviously, it's not like they will not form the ions, but you will, like the value which you will get is not only for one particular atom. It's an influence of so many atoms on this particular atom, and then you'll get the value. And obviously that's not a correct value, right? But if I have only one atom, that atom's influence, or say that nucleus's influence on that electron, is the only thing that is required for me to calculate the ionization enthalpy. Okay, that is why we say that we have to go only for gaseous atoms. Very good question. Sir. Right, I hope everybody understood. This is a very important question. I hope this is helpful for everybody. Right?
Sir?
Yeah, tell me.
Sir, could you explain again why not for aqueous solution?
Yeah, aqueous solution. Okay, aqueous solution ions are formed, right? But when I want to calculate ionization enthalpy, I will take only gaseous atoms. That's what I'm telling. Is the point clear? You're asking why am I not using aqueous solutions for
Yes, sir.
calculating ionization enthalpy? Okay, so that is because other than in an aqueous solution, there are other energies involved. If you go to thermodynamics, maybe you'll get a better picture. Like it's not only ionization energy, there is something called as solvation energy, which will come into the picture when I go for aqueous solution. Okay, and you will study more about this term solvation energy when I go for thermodynamics and chemical bonding, obviously. Okay, so obviously the energy value which you'll be getting is not only ionization energy, it will be IE plus SE. That's the energy you will be getting. So again, there'll be a lot of confusion there. That's why we go on exclusively for gaseous atoms. Yes, there's an answer your question. Don't worry, you like these questions, you will be the why not aqueous solution I'm calculating and how in aqueous solution I'm able to form ions easily. All these questions we'll try to answer in the upcoming chapters. Okay, but now again, it will take a lot of time if I try to explain you now, but you will get those answers, don't worry. Okay.
Sir,
Right? Yeah, tell me.
is aqueous state and molten state the same?
No. They're not same. See, when I say NaCl molten and NaCl aqueous, they are not same. NaCl molten is basically liquid NaCl. Right, that's it. NaCl in pure liquid form is what is molten NaCl. When I say aqueous solution, basically I have solid NaCl dissolved in water.
Okay, sir.
That's the difference here.
So the solvent is water.
Solvent is water, exactly. Here there is no solvent; it's one pure liquid. Here it's
Okay,
a solution. That's the difference between these two. Yeah.
Okay, sir.
Okay. Anybody has any other question? Okay, fine. So now we can move on. So we saw about electropositivity. So now we talked so much about removal of electron till now, right? In the form of ionization energy, in the form of electropositivity. Now we'll move on to the case where I have to add electron into the atom. We'll see what happens there. Okay, right. Fine. Okay, actually, I have to add some more points here. Like since we spoke about electropositivity, now you understand, right? So when I have the entire periodic table, right? When I have the periodic table, so obviously the first two groups, group 1 and group 2, are entirely metals. Right? Group 1 and group 2 are entirely metals. Because what I told you, along the period, electropositivity decreases means the metallic property or the metallic nature decreases. Is it not? Electropositivity decreases means the metallic nature also decreases. So obviously, when the left-hand side, the left-hand corner of the periodic table are always very highly reactive metals, and say in between this, when obviously you have the D block are moderately reactive metals. But when I go from group 13 to group 18, or forget group 18, for group 18, nothing, they are not metals, they are not metals, they are inert elements, right? So till group 13 to group 17, most of them are non-metals. Because again, it makes sense, right? From if you go along the period, the metallic nature decreases, or I can say the non-metallic nature increases. We'll speak about it. We'll also speak about non-metallic nature, right? So, yes, any questions?
Yes, sir.
Yeah.
Sir, should hydrogen be included in the metals?
Yeah. No, that's a controversy again, because hydrogen can form positive ion also, it can form a negative ion also, right? So it can form H plus, H minus. So yeah, that is why it is somewhere on the top, right? It is not in this, not in this, right? So yeah, that we can always debate on that.
Sir, but then in textbooks, they have given it in the group 1, sir. Why is it like that?
No. They will not give it in group 1. Like say they would have given it on top of group 1. There'll be a gap between these two. You will always see that, right? Did you see that? Even though they have given hydrogen in group 1, but there'll be a gap between hydrogen and lithium. Lithium will be in the same period. The same group lithium will be there. But between hydrogen and lithium, there'll be a gap. There will be only one box, hydrogen, gap, and then it comes, hydrogen and lithium comes. But actually, it should not be placed here. If you look at the perfectly IUPAC approved periodic table, hydrogen will be somewhere here, like in between, like there is no connection between the periodic table and hydrogen. It's like that. That's how it will be. Okay.
Sir, so can you
But
tell whether metals are more electropositive or hydrogen is more electropositive?
depends, right? Depends. So like say, as you say, copper is a metal, right? Sodium is a metal. Hydrogen is a hydrogen leave. It's somewhere. It's more. It's
In
both
between,
a
sir.
metal and a non-metal, right? It's both a metal and a non-metal. We'll keep it like that. Okay, so now obviously what you understand, sodium is more electropositive than hydrogen, but copper is less electropositive than, copper is less electropositive than hydrogen. So again, that comes from all the properties which you have to take, how easily the element can lose electron. There are other factors. Hydrogen already is in gaseous state, so I don't have to spend energy on converting the solid to gas or liquid to gas, right? So all these things are there already in calculating ionization energy. Okay.
Okay, sir.
Right. Fine. So yes, that's what. So now in the leftmost corner of the periodic table, you have elements. You have metals, right? But from group 13 to group 17, all are non-metals. Okay. Now in group 13 also, right? Or say for example, I take nitrogen family, nitrogen, phosphorus, arsenic, bismuth, astatine, I think, right? The 5 elements you take. So obviously, when I compare the metallic nature of all of them, obviously metallic nature down the group increases, correct? So phosphorus is more of a metal than nitrogen, and arsenic will be obviously, this is how the order goes. Okay, astatine is a perfect metal, right? Even though it belongs to group 13, I told you group 13 to 17 almost are non-metals, but remember in group 14 to group 17, the last period which I have, right? The last period elements are always metals. Okay, but again, not for everything. I'm just telling you a generalized statement. Okay, generally the last period elements are little more towards metal. Okay, now if I see bismuth and arsenic, I think arsenic is AS or argon is AS. Okay, anyways, I'm not I think it's AT for astatine. Anyways, no problem. So now when I compare this bismuth and arsenic, if you look at them, there are certain elements in the periodic table called as metalloids. Okay, so metalloids are say in between metals and non-metals. They can form positive, like how hydrogen is, right? They can form positive ions also, they can form negative ions also to some extent. Okay, so again, it all depends on the electropositivity. So now, all you have to understand is along the period it decreases, down the group it increases. So now even though it's a non-metal group, like nitrogen is a perfect non-metal, right? Phosphorus will be little okay. This is again, I would still consider as a non-metal only, right? But arsenic, bismuth are metalloids. Again, you'll see astatine is a metal now. Okay, now I think same goes with group 13. If you check group 13, that is boron family, boron, aluminium, gallium, what are, I forgot the other 2 elements. Anybody know the other 2 elements? Boron, aluminium, gallium. Then okay, fine, no issues. What are the other 2 elements, right? So now this is, I would say, boron is again okay. Aluminium is obviously a metal, we know that, right? Gallium is again a metalloid. And gallium is a metalloid. Okay, so like that it happens, right? So this is what I want to tell. So what I wanted to tell is left hand side of the periodic table is entirely metals. Right hand of the periodic table is entirely non-metals. But again, when I go to the right hand side, when I go down the group, the metallic character increases. There might be some metals, there might be some metalloids. All these things are possible when it comes to the right hand side, the P block elements. Okay, this is the point I wanted to tell you, right? Okay, moving on. So now we spoke so much about a removal of electrons. We'll spend some time on addition of electron to the atom. We'll see what happens there. So now we'll look at the energy conservation first. Okay, since how we spoke about ionization enthalpy first, because we're talking about energy required to remove electron. Like that here we'll speak something like that. Okay, so I want to speak the trend which is called electron gain enthalpy. Okay, electron gain enthalpy. Okay, in short form, it is also called as EGE. It's similar to ionization enthalpy, but again, the definition is going to be different. Okay, now go for it. Take down the definition, people, for electron gain enthalpy. It is the energy released. It is the energy released or absorbed, or absorbed. It is the energy released or absorbed when an electron is added, when an electron is added to the valence shell, of a gaseous atom, Okay, let me repeat the statement, people. Right, it is the energy absorbed or released, right, when an electron is added to the valence shell of a gaseous atom. Very, very simple. Right, now when it was ionization enthalpy, right, when it was ionization energy, I just said it is the energy required. That means how much amount of energy is absorbed for me to remove the electron. For me to remove the electron, it is always an endothermic process. What do we mean endothermic? Energy absorbing process. Okay, but now you look at it. Now from the definitions you can understand, when I add an electron, right, when I add an electron, it can be exothermic or it can be endothermic, depending on what atom are you speaking about. Okay, depending on what atom are you speaking about. Okay, now like this point is very clear, I guess, right? If you add electron to the atom, depending on what the atom is, either you have to supply energy for adding the electron, or by adding the electron, the energy is released. Okay, now tell me, say we'll speak about the case energy is getting released. Okay, so I add an electron, energy is getting released from, like say, from where the energy is coming from, or who's, like say, when I say energy is released, from where or by what, and what is losing energy? What is losing energy? Me, you, what?
Sir,
They
is
understand
that the atom?
Yes. I think not everybody understood the question. When I add an electron to an atom, right, I say that energy is released. Who is losing energy or energy? When I say energy is lost, who lost the energy? Obviously, it is the atom which lost the energy. Okay, now if energy is lost, what can you tell about the atom? If an atom loses energy, why is it losing the energy? In general, what are the reasons can you think about?
Because the atom is electronegative.
Because the atom is electronegative? No, forget about the fact that I added electron. Generally, if I see something I'm doing, right, something is happening to the atom and the atom is losing energy. So what is happening? Like what can you tell about that?
Sir, suppose the valency of the atom is 1. Like suppose the atom only requires 1 electron to become stable. So suppose the energy, yes sir, suppose the energy is 500 joules, suppose, when the electron is not added. And when the electron is added, it becomes stable. That means less energy is there. So the energy becomes 300 joules, suppose, and therefore it loses energy.
Correct. So the word which I'm expecting, if anything loses energy, not an atom, if anything, anybody, like any human being or any subatomic particle, anything for that matter, when I say it loses energy, that means it is becoming more stable. Remember this. Okay, Remember this, that whenever I say that when the atom is losing energy, that means the atom is becoming more stable. Okay, because I have already mentioned this point to you, I guess. Energy and stability are inversely related. This is one. Okay, energy and stability are inversely related. Right? So by doing a process, like into the process in this case is adding electron, by adding an electron, if I find that the element is or the atom is losing energy, that means the addition of electron is a very favorable process, in the sense that when I add electron, the species is becoming stable. Okay, now you can ask me, sir, I have Na. Na is becoming Na plus. Obviously, it is becoming stable, right? When I compare Na and Na plus, like say electronically, obviously Na is more stable. Na plus is more stable. But still, for me to form Na plus from Na, I have to supply energy. Now, can anybody tell me this? Why is it like that? So, what I told you, when the atoms become, when I do some process and the atom becomes stable, the atom loses energy, right? But the same thing is happening here. I form Na plus, which is stable, right? But still I have to supply energy. Anybody wants to comment on this point?
Sir, because Na is already stable, right? So we have to supply energy.
Not exactly. No.
Sir, could you repeat the question?
So I'm telling you, for example, right, say Cl to Cl or generally, or forget about it. I'm telling you that I'm adding electron and the atom becomes more stable and it loses energy. And why did I tell you that? Because when I add electron, that particular atom becomes more stable. That is why it is losing energy. Correct? Now, look at this process. I form Na plus from Na. Na is more stable than Na. Obviously, this is a cation. Obviously, neutral species are more stable, but electronically, in terms of electronic configuration wise, right? Na plus is more stable than Na, right? But still, I am telling that I have to supply energy for this process to happen. That basically is the ionization energy which I have to supply. So energy is, so I told you that for becoming stable, energy is getting released, but this is becoming stable, but I am supplying energy to this. Like that's what I'm asking. There is a confusion there, right? Anybody wants to clear the confusion there?
Sir, because we are removing the electron, that's why we are supplying energy, right?
Okay, fine. But still it is becoming stable, correct?
So because, sir, the electron is present, like there is penetrating effect. So, not penetrating, the
nuclear charge.
The nuclear charge, the force of attraction of the proton. So we have to overcome the force of attraction of the neutron.
Yes.
So
Okay, correct.
nucleus.
Yes.
So that's why we are supplying energy.
Correct. Obviously, that's the point. I have to remove electrons, so I have to overcome the force of attraction. So I'm supplying energy. But what about this? It is getting stable, right? So do you think some amount of energy is released in this process? It is becoming stable, correct? The atom. So is it that some amount of energy is released? Or
yes,
what
sir.
do you think? Okay, the answer is yes, it will be released. Okay, since the atom is becoming more stable. Now look at this. You can look into you can see this process is as a two-step process. Okay, I can see this as a two-step process. First thing is that, say I have the electron. Now the force of attraction is there. You have to overcome the force of attraction. Okay, you have to overcome the force of attraction. And the first step would be to say the electron is in the process of coming out. That's the first step, right? Second step, obviously for that you have to supply energy, ionization energy. This is what we speak about, right? But once the electron is completely lost, now when the transformation of Na to Na plus is complete, when this happens, obviously during this process energy is released. Okay, but that energy we don't take into account generally. But yeah, there is some amount of energy released that makes it more stable. Okay, right? But in this case, yeah, tell me.
Sir, can we say that along with the electron, the energy is released?
Along with the electron, the energy is released. We can tell that. Actually, yeah. See, if you can think about it like this. We studied photoelectric effect, isn't it? Right. So in photoelectric effect, this exact same thing was only happening, right? I have to supply energy equal to ionization energy, then the electron comes out. Okay, but if I supply energy more than the ionization energy, what happens? I have kinetic energy of electron also involved. Yeah, it is correlated. It is all connected there. Yes.
Okay, sir.
Okay. Right. Fine. So
Sir?
that's, yeah. Please tell me.
Like, is this energy the excess of the energy which we have applied for ionization energy?
Is this the energy which we have applied? No. If you apply excess, let's say if you supply more energy than the ionization energy, then you'll end up that energy will be transferred to the electron. That will transfer with more speed or more momentum and stuff, right? But this energy is a constant value. Whether you supply exactly ionization energy or you more or whatever you do, this, say for example, it is 100 joules which is getting released. This will be a constant value irrespective of what you send here, right? If you
Sir,
send
I have a
excess,
doubt.
1 second. If you just send excess, that will be transferred to the electron which is coming out, and the electron will have more kinetic energy. That's what will happen.
Okay, sir.
Right? Yes. Your question, Subhrajit?
Yes, sir. Sir, suppose in the valence shell there are 2 electrons present. So if I supply enough energy, can I remove both the electrons at the same time?
Yeah, like say if I tell that the ionization energy 1 is say some 200 joules, and ionization energy is 2, second ionization energy is some 300 joules. So totally, if you supply say 500 joules, yes, 2 electrons can be removed
Sir, at the same time they'll be removed.
at the same time. I mean, no, basically when I reach 200 joules, the first electron will be removed, and after that, the second electron will be removed. But the thing is, you will be supplying it as a chunk, one chunk of 500 joules of energy. Yes, I think at that time two electrons will be removed simultaneously. Yes, correct. Okay.
100. Then,
Sorry? What is the question?
yes, sir. Can you?
I'm not able to hear you. Your voice is breaking, Kanna. Okay, can you?
Now, can you hear me, sir?
Yeah, I can hear you. Tell me.
Yes, sir. So initially, if I supply 500 joules, then the first electron will be obviously removed, but then some amount of energy will also be supplied to the electron, and the
Kinetic
kinetic,
energy.
the kinetic
Absolutely.
energy will be there. Right? So
Absolutely.
how will the second electron be removed with
So
500
the thing is, see, when I have 2 electrons like this, so when you supply 500 joules, initially both the electrons will absorb this energy. Okay, and both the electrons will first try to come out of the nucleus, and then only still if I have excess energy, then you can talk about the kinetic energy. Yes, do you get the point?
Yes, sir. Understood.
Okay, right.
Sir?
Good. Yeah, tell me.
Sir, I can understand why like energy is produced when we add electron, but in this case of Na to Na plus, why is energy getting released?
Why is energy getting released? That's what, no, like when this is because this is becoming stable, right? So it's not like a lot of amount of energy is released, but a considerable amount of energy is getting released. Say there is this thing called as, when you go to thermodynamics, it will make more sense, but still I'll tell you now, there is something called as lattice enthalpy. Okay, lattice energy. Okay, so what happens is, like say I have Na plus and Cl minus, that only forms the crystal, right?
Yes,
Okay.
sir.
So this Na plus and Cl minus will come together and make a bond. There'll be some kind of bond formation happening here. Okay. So whenever bond formation happens, you will eventually release energy. Energy is released. Okay. Right. Now it is not only because energy, the bond is forming between the sodium and chlorine. That's why energy is getting released. In this process, right? Obviously, you would have started with sodium, and you would have ended up with this, and you would have started with Cl, you would have ended up with this, right? So overall, there will be so many things happening inside. You will see there is something called as Born-Haber cycle. You will see so many of them. So at the end, if you see like say putting all the subtraction and addition, all the subtraction of energies, addition of energies depending on what kind of process we are doing, right? At the end, we say that the energy is getting released. Okay, so like that, here also the overall thing, if you see, obviously the energy is getting supplied, ionization energy, right? But but because of that, you cannot, what to say, you cannot deny the fact that some amount of energy is getting released also, because the fact that this is becoming stable, that is Na plus is more stable than Na. You cannot deny the fact. If you cannot deny the fact, obviously this amount of energy is obviously released. But that compared to the amount of ionization energy you spend might be very, very less, even negligible, right? But still, this energy is getting released because Na plus is becoming stable. That's the point.
Sir, energy is inversely proportional to stability. So
Yes.
if Na plus is more stable, then energy should be very much negligible, right?
It cannot, in the sense that, say, for example, if the potential energy of sodium, I'm just giving you some random value, potential energy of sodium was some 500 joules, right? But the potential energy of this thing would be 400 joules. That's it. That's how it will be. It will not be like it will become zero. If it becomes zero, right? If it becomes zero, like all the electrons will stop moving, right? The electrons will not revolve around the nucleus. Any type of motion for that matter. Say, for example, if Na plus ion is surrounded by a water molecule, right? Now, if say, for example, I put salt in water and you try to conduct electricity to it, electricity will get conducted, right? Why? Because the Na plus ions are moving inside. If they have zero energy, that means they are dormant, they are dead. That's what it means when I have zero energy. Okay? Like zero energy is not a case which you can talk about. Even if something is at rest, right? Even if something is at rest, we say that it has an amount of potential energy. Having the cause of zero energy itself is a debate, itself is a research topic. Like zero energy, or when I go to 0 Kelvin, all these things are, debatable topics. Okay, 0 Kelvin is not reachable. According to the second law of thermodynamics, you cannot reach 0 Kelvin. We'll study about more of these. There's all these energy considerations, all the questions you have, you can ask me more and more questions when you go to thermodynamics. Beautiful chapter, such a beautiful chapter. We'll see more about it. We'll see more of it in those chapters. Okay, but anyways, answering the question. Did you get the answer to the question?
Not satisfied.
What was exactly the question you asked?
Like here, obviously, it is obvious that Na plus won't be 0 joules, sir. But why is energy getting released?
Why is energy getting released? In the sense, because Na is becoming stable, right? Sodium is not exactly in sodium form. It is becoming Na plus. It's becoming some other species, which is more stable than sodium. So obviously, how it will become stable? When I say stable, that means obviously the only way it can become stable is by losing energy. That's the only way. Okay, first, do you accept the fact that Na plus is more stable than Na? Yes or no?
How, sir?
How? I mean, electronically, like say, according to the octet rule and stuff, this is octet stabilized.
Yes, sir.
Right?
Na is more stable. Yes, sir.
So Na plus is more stable than Na. Now, when I say stable, when I say something is attaining stability, the only way can something like energetically speaking, obviously the process, what you do is different, but energetically speaking, if something has to become stable, it has to lose energy. That's the only possible way in terms of energy. By gaining energy, you cannot become stable. No, that is never a possibility. Yes, that makes sense.
Sir. Yes, sir.
Okay, right. Okay, so why did we speak about all this? Okay, so we speak about why is it that okay, going back to the definition. What is the time, people? We are spending a lot. Okay, we have half an hour. Right. So I was telling the definition of electron gain enthalpy. It says that it is the energy gained or energy lost when an electron is added to the valence shell of a gaseous atom. Right. I think this thing is very dark. Let me put some light. Okay, that's better. Right. So that happens. Right. Okay. So moving on, like now we understood the definition. Now moving on, why is it that some elements are getting some elements are getting stabilized, in the sense that some elements are losing energy and some elements are gaining energy? It obviously depends on the atom, right? So now if the atom becomes stable, right, if the atom becomes stable by adding electron, then energy will be released, right? But same thing, if the atom becomes unstable by adding an electron, then energy will be absorbed. Okay, because obviously it is becoming unstable. Still you want to add an electron. If you want to do that, you're going against nature. So obviously you have to supply energy there. Okay, right. Now there are other reasons also for this energy getting absorbed. One, this thing is obviously unstable, right? Now the other case for the energy to be absorbed is repulsion. Now you look at this. When I'm adding electrons, say when the incoming electron comes, right? Now there'll be already existing electron inside the atom. Correct? There'll be already say 10 electrons or 12 electrons or whatever be the number of electrons is already being inside. Correct? Right? Now you have to, when the incoming electron comes, now the incoming electron and the existing electrons will have repulsion. Okay, now you have to overcome the repulsion. You have to push the electron against this repulsion and then add it. So that might also be sometimes resulting in energy getting absorbed. Okay, so fine. So energy absorbed during the electron addition process can be because of two cases. First case, the atom is becoming unstable by the process, right? So obviously when I compare Na and Na minus, you have to add an electron here to become Na minus. Obviously it is unstable. So thereby obviously energy will be absorbed. Or the second reason is sometimes the repulsion will be too much that you have to supply energy for it to go inside. For the electron to go inside to overcome the repulsion and to go inside, you have to spend some energy. Two reasons are there, right? But only one reason for energy being released. That is obviously the atom becoming stable by adding an electron. Okay, right? Fine. So keeping that in mind, right? Keeping that in mind, if obviously whatever happened, if you can understand. Actually, yeah, please tell me.
Sir, I have a doubt regarding this. If atom becomes unstable by adding electron, it basically loses its stability.
Exactly.
So it has to lose energy to become stable, right? Why is it absorbing energy?
It has to lose energy to become stable. If it is becoming unstable,
it is already unstable, right?
No. You are making it unstable. You are making it unstable by adding electron. So obviously, if you are only making it unstable, you only have to take the cost of energy. That means you only have to supply energy for this reaction to happen, for this process to happen. That's how you see it. Yes, makes sense?
I'll ask later, sir.
Okay, fine, right, no problem. Right, or if at all I have to answer you again, the atom is becoming unstable. Na is becoming Na minus is a not favorable process. Right, Na minus is way unstable than Na. Right, so now you know that this is a very tough process in the sense that this is an unfavorable process. Now this leads to instability. Now see, how do I put it? Now say, for example, if I have to speak about which, like, say you must have spoken of this thing, say helium ions. Okay, say if I want to store helium ions, okay, or say if I want to store hydrogen ions, right? If I have to store hydrogen ions, obviously you have to spend a lot of energy on that if you have to store it, right? Why? It's because H plus ions are unstable, in the sense that if you want, they are okay. We'll not have to go into details. The H plus ions are very unstable, right? So now if you want to store it, you have to supply energy. Same way, if you want to make sure that Na minus keeps on existing, right, you have to keep on spending energy on this process. Then only Na minus will keep on existing. Or else what will happen? Naturally, everything wants to be stable, right? Say you supply some energy, you make Na minus. Okay, but now the moment you stop supplying energy, Na minus will go back to Na, because that is the naturally energetically favorable place for Na to be. Do you understand? I think this correlates to the question you're asking. Is it fine?
Yes, sir. So like, so can you draw some noble gas?
Noble gas. Yeah, I can write some noble gas. Say neon. I
yes,
sir. Okay.
Yes, sir. So if we add one electron, like the electron will be added to the same shell or a new shell?
Depends. Say here in this case already in the thing everything is filled, right? So obviously the incoming electron will add to the next shell, like the whatever shell is empty, that shell only will get added.
Yes, sir. So now to become stable, it has to lose that electron, right?
Exactly, correct.
For
To
that,
become
again, we
stable,
have to supply energy.
no. This case, you like see, this case, I don't have to spend energy. Now, why? Because even though you see that this electron is having, say, once you added it, once you got into the field of this nucleus, obviously there will be some force of attraction, right? But this is very highly unstable, that the force which is here is not enough for me to hold it in the same place. So what will happen is the unstability the unstability cannot be compensated by the force here. So what will happen? Naturally, even though you don't have to supply any energy, but the electron will eventually be lost. That's it. But if at all you want to keep the electron here and make it Ne minus, then you have to keep on supplying energy. Keep on supplying energy to this. That's what will happen.
Okay, sir.
Okay, right?
Yes, sir.
Fine. These are all, see, hypothetical situation you're talking about. Okay, in reality, none of the things which we asked, none of the things which we spoke about now will never ever going to happen. If it happens, yes, this is how we predict it to be. Okay, good discussions, actually, very good discussions we are having, right? For the class which you are in, and for the amount of discussions we are having, I'm really happy, right? Even though we are not covering up on the topics which you have to cover, but still these are nice discussions. I hope now nobody is getting bored by these discussions. Is there anybody who's getting bored by these discussions? Like, I hope it shouldn't be the case, because say something, you maybe we didn't think about the question, but someone else is thinking about the question and they are asking, and then you are getting benefited out of it. It's like something comes free, right? You should enjoy it. It's not like it's not boring, right? Everybody is able to understand what question they're asking. Everybody is able to understand what explanation I'm trying to give. Correct. So everybody, like, if at all, like it's someone's question and I'm answering, and if you want, and someone else want to add a point, you are always welcome to add a point. You don't have to keep mom say it is his question and Sar is answering. No, it is always a classroom discussion. Okay, so fine. I'm really happy about it, but the only fact is that we have to cover some portions also, but not a big deal. We can even have extra classes and do that. Not a big deal at all. Okay, fine. So yes, so we saw by adding electron, if it becomes stable, the energy is getting released. For energy getting absorbed, there are two reasons. One thing is the atom becoming unstable, and obviously the second reason is the repulsion between the incoming electron and the existing electrons. Okay, right. And I wanted to remember one sign convention. Right, this sign convention will be using not only here, in all the processes, especially in thermodynamics, you will be using the sign convention a lot. Now remember this, whenever we speak about energy getting released, right, now that will be a positive value. Sorry, that will be a negative value. Okay, and whenever we see that energy is getting absorbed, right, that would be a positive value. Okay, say for example, I tell that during a process, something happens and something loses 500 joules, 500 joules of energy lost, then I will tell the energy value is minus 500 joules. Okay, and same way, if I tell that 500 joules of energy is gained, I will tell that the energy value is plus 500 joules. This you have to remember. Okay, energy released is a negative value, energy absorbed is a positive value. Okay, so because now we are talking about energy getting released and energy getting absorbed, the sign conventions are also very, very important. Right? Okay, so now we'll try to understand what happens down the group. What is the time, people? Okay, 10 more minutes, right? So we'll see what happens when I go down the group and along the period, what happens to electron gain enthalpy. Okay, right. Now, please understand, when I go down the group, obviously metallic character increases. They will not be able to gain electron. Or you can, if at all you speak logically, we don't have to make it into so much chemical terms. We can speak logically. Say when I go down the group, lithium, beryllium, sorry, not beryllium, lithium, sodium, potassium, if I take, obviously the size increases. Right, the size increases. So now, see, I have one shell I have two shells. Now I'm trying to add one electron here. I'm trying to add one electron here. Now, obviously, in this case, it's a little more easy, right? Is it not? Because when the electron comes, this nucleus and this electron will be little close, so that when the electron comes somewhere, not exactly on the shell, but somewhere nearby itself, this nucleus will be able to catch hold of this electron, right? But in this case, yes, it will happen, but the distance is little far away, so it will not be that strong a force that I had in this case. Okay, here the force is higher force. Here the force will be little less compared to the previous case, right? So obviously adding electron in this case is little easier than compared to this case, right? So as the size increases, right? As the size increases, adding electron becomes more and more and more difficult, because obviously the nucleus will not be able to catch hold of the electron if the incoming electron is very far away from it. Okay, so now what happens here, when I go down the group, right, the EGE becomes more positive, or I would say it becomes less negative. I think it makes sense, right? So when I say when it is more and more difficult for me to add an electron, obviously the more and more energy has to be supplied for the electron to get added. That means obviously more and more positive, or it is going to become less and less negative, depending on what group you're talking about, right? So if I speak about group 1, obviously all are metals. Already, say for example, lithium is having electron gain enthalpy of 500 joules plus 500 joules. That means for you to add electron, you have to supply 500 joules, right? Say for sodium, it would have been say 600 joules. That means for you to add an electron, you have to supply 600 joules. For potassium, it would have been say 700 joules. For you to add an electron, you have to supply 700 joules. But say in the case of say chlorine, bromine, and iodine, if I take, why didn't I write fluorine? I'll come to that point. Okay, there is an assumption there. We'll come to that point. Okay, fine. So when I compare chlorine, bromine, iodine, say chlorine has minus 500 joules. That means when I add electron, 500 joules of energy is getting released, right? Say bromine will have minus 400 joules, in the sense that when I add electron, only 400 joules of energy is coming out. And say for iodine, it will become minus 300 joules, right? That means when I add electron, only 300 joules of energy is coming out. Hope you understand. By the point, more power, when I go down the group, EG becomes more positive, and like more and more positive and less negative. Okay, that's what happens when I go along down the group. Okay, I hope this makes very good sense, what I'm trying to say. Okay, I didn't say increase or decrease. Increase or decrease doesn't make sense here. Okay, you should always say that it is becoming more positive or less and less negative. That's it.
So,
Okay.
so in case of metals, energy is always absorbed.
Obviously absorbed. Yes. In case of metal, when I add an electron, energy is always absorbed. No, like obviously for all metals. Yes. But for non-metals, they will have a negative value of Eg. Correct. Yes.
About noble gas?
Noble gas obviously will have positive. Both ionization,
Yes, sir.
ionization
Okay.
energy is obviously positive. Electron enthalpy is obviously positive. No doubt.
Okay, sir.
Right. So now when I go along the period, now same thing, same explanation can be given, right? So it's about the size. When I go along the period, size decreases. So it is more and more easy for me to add an electron. So now along the period, Eg becomes, okay, fine, I'll write down. Eg becomes more negative and less positive. Right? This you can say. That means when I go along the period, when I, for example, again, I don't have to, I think, talk about this, right? Now, this, if you understood what do you mean by more positive and less negative, now again, you can understand more negative means when I add electron, more amount of energy is released. And when I add electron, less amount of energy is supplied. That's what you mean by this more negative and less positive Eg values. I hope everybody is able to understand what I'm trying to say. Okay, right. Now, this we understood, right? Now, keeping this in mind, if at all I give you certain elements, you will be able to arrange them in the order of electron gain enthalpy. But when I go to this one, That is I think nitrogen, phosphorus, oxygen, sulfur, fluorine, chlorine. Now for this 6 elements alone, there are little problems. Okay. Now what is the problem? Now what did I tell you? When I go down the group, right? Now it is going to become, all these are non-metals, no doubt about it, right? Now when I go down the group, the Eg value becomes less and less negative. For example, say for nitrogen, if I assume that the Ag value is minus 500 joules, now this should have been minus 400 joules. Okay, that is what we expect, right? But what we see in reality is not the case, right? What I see in reality is the opposite. This is minus 400. See, I'm not giving you exact values, guys. Please do not think that these are exact values. I'm just giving you a number so that you'll understand. Okay, so if this nitrogen value is minus 400, this value was minus 500. And same goes here. Say, for example, now this value was minus 600 joules. And this value was minus 700 joules. Same way here, the value was minus 800 joules. And this value is, say, minus 900 joules. Now, this happens only between the second and the third period. This is my second period. This is my sorry, I'll write this as P2, second period, and this is my third period, P3. This happens only for period 2 and period 3 and not for anything else. Okay, now why this happens is the question. Okay, now if at all I need, especially I would say for nitrogen and phosphorus, these are almost equal values. Like I would say it's not 400 and 500, I just gave you this thing, but I would say EGE of nitrogen is equal to Eg, almost, not exactly, almost approximately equal to that of phosphorus. But for these 4, that is oxygen, sulfur, fluorine, chlorine, for these oxygen, sulfur, these 2 pairs, right, it actually becomes, like say sulfur is having more electron gain enthalpy than that of oxygen, in the sense more negative value. Same way, chlorine is having more negative value of Eg than fluorine. Now you have to account for it. Or even why is it equal also? If at all I understand, if I explain these 2, that is also understood. Right, now why this happens? Now, for me to understand why this happens, I have to go back to the reason of why the energy can be absorbed, or energy, or when I say energy absorbed, I would say it is more positive and less negative. Now, why? What are all the reasons it is? What are all the reasons it will be there? Obviously, because the atom becomes unstable, and the second reason is this repulsion. Okay. Now, what happens is, even though I know fluorine is very highly electronegative, right? But its size, now you know, when I go down along the period, its size decreases. Fluorine is one of the elements who are having one of the smallest size in the periodic table. Okay, one of the very smallest size. Okay, so now when I'm going, so what happens here? In a very small size, very small area, I have 9 electrons. Okay, when in a very small size, I have 9 electron. So if I have to add an electron, the charge density, right? The charge, what do you mean by density? When I say, okay, answer me this question. I don't know how many of you, China is a very big country. Like say, China is like 5 times, 6 times bigger than size of India. Okay, right? Population is, but population is only like say 2 crores, 3 crores more than India. Not even times. It is little 1 or 2 crores this thing at India. So which is a densely populated country, India or China?
India.
India, right? Smaller space, very huge amount of people. Assume that the population of India and China is almost equal. I will not even say China is not that much far and all. Okay, India and China are almost having similar population, but the size of India is little smaller compared to China, right? But so I would say India is having more population density, right? Same way, fluorine is having very high charge density in the sense that in the form of electrons. Very small space, in that I need to have 9 electrons. That means I have already very high charge density. Okay, so the incoming electron will suffer a lot of repulsion because of this high charge density. So that's why even then it's a negative value, obviously, it's a negative value only, but still when I compare it to chlorine, it is still a little smaller negative value. That's what you need to understand. Now, why, if someone asks you, arrange, say
Sir,
yeah, 1 second, I'll just complete this. Fluorine, chlorine, bromine, iodine in the EG value, you should tell that this thing, chlorine is having higher than fluorine, then this is the order. This is how the order goes. So in this particular group, chlorine has the highest EG. Same way, in this oxygen, sulfur, then selenium group, sulfur is the one which will have the highest EG. Now, the reason to this is the inter-electronic repulsion. You should write this word if this question comes to you, right? The question will be like this. Even though fluorine is the most electronegative element in the periodic table, the electron gain enthalpy of fluorine is lesser than that of chlorine. Why? They will ask you. You should tell that since the fluorine has a very small size, it has very high charge density, right? So the incoming electron will suffer more repulsion than in the case of chlorine. That is why the EG value is little less. And same goes with oxygen and fluorine. Same goes with nitrogen and phosphorus. Okay. Yes, Suprajit, your question.
Sir, this logic also works for magnesium and beryllium.
This logic even works for beryllium and magnesium. No, not like that, because beryllium is like, see, this happens now. Why in this side of the periodic table? Because already the size is already keeping on decreasing. There, beryllium is having a decent enough size. It's not as small as these three atoms. Okay. So if the atom is very small, only then this kind of problem comes. The beryllium is decently big enough. So it's okay.
Okay, sir.
Right? Fine.
Sir?
I think yeah, please tell me.
Sir, then even in case of nitrogen and phosphorus, if we add an electron to nitrogen and if we add an electron to the phosphorus, nitrogen will have more density, right?
Yes.
More
yes.
charge density.
Yes.
Yes, sir. So the energy should be more, right? In case of nitrogen, why is it comparatively equal to phosphorus?
Oh, like the thing is here, the size, like say, that's what, like here, why is it like this? Say now, if you look at the difference here between oxygen and sulfur, say for example, the difference is only 50. Okay. But between fluorine and chlorine, the difference is 100. Okay. So you see what is happening here. When I go like this towards the left, the difference keeps on decreasing. Like that's what happens there. So obviously, when I compare beryllium and aluminum, beryllium will have a better EG value. So that's not beryllium, boron. Boron will have a higher EG value than this thing. So hope you're trying to understand. It's because of size again. The smaller and smaller the size becomes, tougher. Like it's not tougher and tougher. The repulsion keeps on increasing. That's what you have to understand. Okay.
Yes, sir.
Right. It's all about the difference here. Here the difference is again not the correct numbers. The random numbers 50, 100. Here it becomes equal. Now when I go just below this, before this thing, I had carbon and silicon. Right there, I don't have this problem. Now what we expect to happen, that's what is happening. When I go down the group, it is becoming less and less negative. Yes, that is happening for carbon and silicon. It is happening for beryllium, boron, and aluminum. Right, but only for this nitrogen, oxygen, fluorine, and the next corresponding elements, only for them this kind of problem is arising because they are very, very small atoms. That's why.
Okay.
Right. Okay, I think we'll stop with this for today. Okay, so I think tomorrow also we have a class. So tomorrow I think I'll try to complete this chapter. Okay, most probably I'll be completing that. I might even start chemical bonding. Right? Any questions anybody has? If not, we'll wind up the class. There's something in the chat which I didn't see. Anything in the chat? Okay, something. Okay, cool. So I think there are no questions. We'll stop it right here. Right? Thank you so much, people. We'll meet again tomorrow.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you. Thank you. Thank you so much.